Hello friends, welcome to our channel. In this lecture, I would like to explain an example based on the singly reinforced rectangular beam. So that is design of a singly reinforced rectangular beam to suit the following data. So all these are the given data. So the given data will be clear span is 3 meters, width of the supports will be 200 mm, working live load is 6 kN per meter, and M20 grade concrete and Fe 450 steel. So take down the given data. So our first step is take down the given data. So clear span. So clear span is given as 3 meters, which is L equal to 3 meters, and width of the support, this step. So that is B equal to 200 mm, and working live load. So working live load will be equal to 6 kilonewton per meter, which I am denoted with LL, 6 kilonewton per meter. Then M20 grade concrete, that is FCK equal to 20 newton per mm square, and Fe 415 steel means Fi equal to 415 newton per mm square. All these are the given data. Based on this data, we are going to design a beam. So already in the question itself, they will clearly mention that singly reinforced beam. So generally the question will comes like this: design a reinforced rectangular beam. So design a rectangular beam to suit the following data. They didn't mention that whether it comes under singly or doubly. So based on the condition, for example, you find out all the moments, and based on the conditions, whether it comes under mu less than mu limit or mu greater than mu limit. So after knowing this condition only, we can go the move to the design, whether it comes under the singly reinforced beam or doubly reinforced beam. For example, after finding this condition, knowing this one mu and mu limit, whether it will be mu less than mu limit means we can prefer singly reinforced design, and mu greater than mu limit means we can prefer doubly reinforced rectangular beam. But here in the question itself, they will directly mention that go for singly reinforced beam. So based on that only you can design this one. Okay. Then our next step is to prefer the cross sectional dimensions. Cross sectional dimensions. So cross sectional dimensions means in this we have to find each and everything like effective depth, overall depth, all the things. So here cross sectional dimensions. So you can select this one based on the span to depth ratios. Span to depth ratios. So that is L by D. So for these types of beams, I will give you some of the note points. See here span to depth ratios for the style sections. For example, your span range will be 3 to 4 meters means you can select span to depth ratios will be 15 to 20. In the same way, your span range will be 5 to 10 means you can select span to depth ratios will be 12 to 15. And if your span range will be greater than 10 meters means you can select L by D ratio will be equal to 12. So all these are the important note points you have to remember before going to the design. If in our question your clear span will be 3 meters, therefore I am taking the range of that particular span will be this 15 to 20, because our span range will be 3 to 4 meters, 3 meters only. For example, if they mention some your span will be some 5, 6, 7, 8 or 10 means we can select L by D will be equal to 12 to 15. So above greater than 10 meters means we can select 12. Okay, so it will be in the range of 15 to 20. 15 to 20. So already we know what about this L. This is clear span, and this one will be effective depth. Okay, therefore based on this I am finding this effective depth. D equal to, I am sending this one, L by 15 to L by 20. So already we people know what is the clear span range, that is L value will be equal to this 3 meters, and in terms of mm it will be 3000 divided by 15 to 3000 by 20. Simplify this one, you will get 2 ones 150 times here 15 2 ja. So like that it will be in the range of 200 to 115 mm. Therefore your effective depth will be 200 to 150 mm. So you can select your effective depth maybe 150, 160, 170, 180, 190 or 200, or else 155, 165, 175, or else you can make this average 200 plus 150 divided by 2, which is exactly 175. Like that also you can select any value, then you can adopt the effective depth. So here I am selecting the effective depth according to our problem. So I am selecting for the trial section which is 160 mm. So if you want you can go for you can prefer 170 mm and go for the design, no problem. And overall depth, so overall depth will be some 200 mm approximately. I am selecting this for our trial section. Okay, so you can select overall depth will be in such a way such that it will covers minimum cover also. So already we people know the minimum cover for beams will be equal to 25 mm. So each and everything I explained in the previous lectures, that is in lecture 1, 2, 3, while explaining the introduction part. So minimum cover for slabs will be 20, beams will be 25, columns will be 40, footings will be 50. So if you add minimum cover for this one means you will get some 25 means above 185. So whatever the effective depth, and again effective cover, so minimum cover will be denoted with some d dash means effective cover. Effective cover means again diameter by 2. So based on that only you can fix the overall depth. So here I am assuming more than that, that is 200 mm. So which I am fixing. For example, minimum cover will be 25 and effective depth will be 160, so 185. So 185 means, for example, in a beam, what is your effective depth? Effective depth will be center of the dia bar to the top, and clear cover will be surface to the bottom. And effective cover will be, for example, if I am assuming some 16 dia bar also, you will get some 8, means here some 15 value will be extra. Even though I assume 30 diabar also, it will be suits. Therefore I am selecting above that value which is 200 mm. Okay, and I am going for the trial section. Then our next step is effective span. Our third step is effective span. Effective span, so I already clearly explained this effective span procedure also for the simply supported beams. So what is the procedure for finding this effective span? So the column is continuous here, so it is better to mention like this. So continuous, so this is the column. So here I am showing the dia bar also. So this is the beam, so I am showing the dia bar. So what is the effective depth? Already we know the effective depth will be taken from the center of the dia bar to the top. So this is the effective depth, and here they will clearly mention that here to here the clear span is 3 meters. So up to the exact of the column. And what about the width of the support? So width of the support is given in our question itself, 200 mm. Or else, so the width of these supports given in the question will be 200 mm. So this one, and here also this one will be 200 mm. So if they will given in the question means it will be okay. Otherwise you can select the width of the beams will be 150, 200, 230, 250 and 300 mm. The width of the beam should be equal or less than the dimensions of the column supporting the beam. Okay, so this is the given data, that is 3 meters clear span, 200 mm width of the support and 200 mm width of the supports, like this. Then what about your clear span? Effective span. Effective span is denoted with LE. Effective span is denoted with LE. So your effective span will be in the range of center to center of supports. That is from the center to the up to the center. So that is 200 divided by 2, which is 100, plus 3000 plus 100. So that one will be equal to 100 plus 3000 plus 100. So overall you will get 3200. And again next point will be clear span plus effective depth. So clear span is given as 3000, that is 3000 plus effective depth which we adopted, that is 160 mm. So that is 160. If you simplify you will get 3160. So in terms of meters it is 3.2 in meters, in terms of meters it will be 3.16. So out of these two we can take whichever is less. So this is the procedure for finding effective span. So effective span will be in the range of center to center of the supports and clear span plus effective depth. You please simplify these two, and out of these two whichever is less you can take down, that is your effective span. Therefore here our effective span will be equal to 3.16 in meters. Then go to the next point, loads. So here our fourth point is loads. Okay, so first consider what are the given loads here. Given loads in the question will be only live load, that is 6 kilonewton per meter. 6 kilonewton per meter, that is live load will be equal to 6 kilonewton per meter. Then always remember, take down dead load of the beam. Dead load means DL, I am denoted with dead load, DL. So that is dead load. So dead load of the member. So for beam, what is the dead load? So that is the property of the beam. For example, that is equal to self weight of any particular member. For example, my self weight, whatever the weight I am. For example, you take any particular material self weight, that is considered as self weight without moving. For example, myself, my weight will be equal to some 60 kgs, like that. And again if I am lifting any books, that comes under the extra load, which is live load, which is moving loads or removable loads. So the live load is different, dead load is different. Self weight means only the dead load means self weight of that particular member. So we are talking here about the beam. So the beam will be generally like this, you can assume. So this is the beam. So I am taking width of the beam like this. So I am showing the beam in three-dimensional view. Okay, like this. I am showing the beam in three-dimensional view. So here already we taken that effective length of this span will be equal to some 3.16 in terms of meter. So already we know the overall depth of the beam, which is 120 mm. But here they will mention live load will be equal to kilonewton per meter. Live load will be kilonewton per meter. Okay. So whatever the loads we are considering, it is for only 1 meter span. Okay, here the overall length will be 3.16, but here live load and whatever the loads we are considering, that is for 1 unit, that is 1 meter here. So self weight will be equal to B into D into its height into unit weight of RCC. So that one will be equal to, what is the B value here? Width of the supports we are considering, that one will be equal to 200 in terms of mm, that is 0.2 in terms of meter. And what is the D here? That is overall D will be considered as 200 mm. Okay, that is 0.2 in terms of meter. Sorry. B into D into L. This one will be L, not H. Why? Because depth in terms of height only. So B into D into L, then only it will covers. Okay. So this is L. So already taken that D value. So B and D will be over. And in terms of length, I am considering just 1 meter span. So this is also in terms of meter, this also in terms of meter, and this also in terms of meter. And what about unit weight of RCC? That unit weight of RCC will be kilonewton per meter cube. If you simplify, you will get the dead load will be in terms of 0.2 into 0.2 into 1 into 25, that is 1 kilonewton. But here we are considering that dead self weight will be only for 1 meter span, therefore per meter. So I think you are getting my point. What I am taking means dead load means self weight of any particular member. So just like I am talking about myself, means my self weight is 60, that is the my dead load, that is my self weight. Like that each and every member has its own self weight. So that one will be equal to the property of that particular material, that is B into D into its length. So overall length of the beam will be 3.16 meters. What about unit weight of RCC? It will be given per meter only, kilonewton per meter cube, like lengthwise, breadthwise and depthwise. So therefore in terms of meter only we have to calculate that self weight, that is I am considering width, depth and 1 per 1 meter span, that is the lengthwise. So therefore the overall self weight per meter will be, so up to here the overall self weight will be equal to 1 kilonewton per meter. Then total load. So if you add these two, live load and dead load, that is 6 plus 1, that one will be equal to 7 kilonewton per meter. Whatever the load you will get according to the limit state condition, so factored load will be equal to 1.5 times of the load. So that one will be equal to 7 into 1.5. So therefore you will get 10.5 kilonewton per meter. So this is the procedure for finding self weight of the beam. So here they didn't mention any extra things. So for example, if you solve slabs or any other things, means maybe sometimes they will given floor finish, plaster finishes, like that. So if you want whatever the in the question they will given loads, means you please consider here, otherwise you just take down dead load. In sometimes live load is not mentioned in the question also, At that time, for residential purpose, live load will be taken some 2 kN per meter, and some office purpose, so live load will be taken for 3 kN or above 4 kN per meter. According to the code, you can consider that one. Okay, then go to the next step, which is moments. So what about this moment? So based on this only, we can consider the condition whether it will be greater than or less than mu limit. So what is mu? So mu will be equal to wl square by 8. So we know that maximum bending moment for a simply supported beam, that one will be equal to wl square by 8. So this is the simply supported beam, and the maximum bending moment will be range of wl square by 8. So already we people know that one. So based on this only, we can consider w. So already we simplified here in the previous step, that one will be equal to this 10.5. And what about this here? So already we calculated effective length. So each and every time we used to take that effective length, that is 3.162 whole square divided by 8. If you simplify this one, definitely you will get 3.1 around kilonewton meter. So your mu value will be equal to 13.1 kilonewton meter. You please simplify this value, you will get definitely this one. Okay, maybe some digits different, 13.1, 12.9, approximate to 13. Okay, then check the mu limit also. So this mu limit will be based on the tension reinforcement. So already I simplified all these things. So whenever M20 grade concrete is given and Fe415 steel is given, so your mu limit will be equal to 0.138 FCK BD square. How you will obtain this? So you please remember this formula directly. How you will obtain this formula? This can be obtained by simplifying the other formula, that is 0.36 FCK B D into, so again liver arm d minus 0.42 xu. So if you substitute the values, then you will get directly this value wherever fck 20 and fi 415. If you substitute that values directly, you will get this one. So it is better to remember always, for M20 grade concrete and Fe 415 steel, your mu limit will be equal to 0.138 fck bd square. So already 0.138, and fck M20 grade will be 20, and b, so width of the support will be given as 200, and d value will be effective depth, so that is 160 whole square. So each and everything you will know. If you simplify, you will get this value is 14.13 kilonewton meter. So check the condition. So here mu value will be 13.1, and mu limit value will be equal to 14.13. So this value is less than this mu limit. So therefore your mu will be less than mu limit. This problem will comes under the design of singly reinforced beam. Okay, so in the question already mentioned that design a singly reinforced beam to suit the following data, but if they are not mentioned like that, means you can come step by step procedure up to here, and here you can see the condition whether it comes under singly reinforced beam or doubly reinforced beam. For sometimes if your mu will be greater than mu limit, means then you can go for the doubly reinforced design. So that is the procedure for singly reinforced step condition, whether you can go for the singly reinforced beam design and doubly reinforced beam design. And after that, go for the tension reinforcement. So I will show you that one also. So already we people know the formula, which was in the page number 96 in the book. So see here, so this is page number 96 in your Indian Standard Code book. So this is your Indian Standard Code book. So here this formula, See here this formula, okay, mu equal to 0.87 Fi area of the steel d into 1 minus area of the steel Fi by BD So take down that formula as it is. Mu will be equal to 0.87 Fy area of the steel into d 1 minus area of the steel Fy by Fck into B into D. So this is the formula, simplified formula, which was in the Indian Standard Code Book, page number 96. So that code book will be 456 2000. So IS 456 2000, page number 96. So this is the simplified formula. So already we people know what is this mu value. So your mu value will be already simplified here, that is this 13.1 kilonewton per meter, kilonewton meter. Okay, so I am taking that one 13.1 into 10 to the power of 6. Okay, so in terms of mm and 0.87, your Fi will be 415, and your, so we want to find the tension reinforcement. So tension reinforcement means here area of the steel only, and again sorry, D value. So what about this D? This D value will be effective depth, that is 160, and again 1 minus, so area of the steel here is unknown, and again 415 by FCK characteristic compressive strength is M20 and B will be 160 and D effective depth will be, so what about your effective depth? Your effective depth will be adopted as 160 and B width of the support will be 200. This is B and this is D and this is FCK. So here if you simplify it by using your scientific calculators means, so it will be get in the form of quadratic equation maybe. Okay, and again simplify that one, so ast whole square minus some ast minus some value. So if you simplify that one, maybe in some calculators you will get directly the area of the steel value, that one will be equal to approximately I am telling, so here I am getting 275 mm square. So if you simplified means you will get maybe some 270 and 276 274, some approximate value which is more or less to near to this number. So this is the area of the steel value, and again you have to check this condition based on the minimum area of the steel. If you want you can check this one, so almost it will be in the safe limit only. I will mention that formula also. Area of the steel minimum will be equal to 0.85 BD by Fi. So already while explaining the concepts I shown this problem, this formula also. If you check this one, so your area of the steel will be greater than this area of the steel minimum. So whatever the value obtained here, area of the steel minimum, it will be lesser than this value only, means minimum steel required here will be, whatever the steel required, it will be greater than that one. So if you want, you please simplify this one directly, you will get. So I will tell you that value also. So the minimum steel will be here 65 around. So the minimum steel required here is 65 around. Okay, so minimum steel is that much is required for this beam. You please simplify, you will get the value also. But here your area of the steel will be greater than that minimum steel. Okay, no problem. So you can proceed with this only. Sometimes your area of the steel will be some around 300 meters, means you are getting some 275, means you can limit this value to here. You can provide minimum steel will be 300 at that time, but here no, you need to do like that. Your area of the steel will be greater than that the minimum required in the beam. So after that continue the problem. See here, after that we have to, so after solving, your area of the steel will be equal to 275 mm square. For this one we are going to find the minimum number of the bars. For this one you are going to find the minimum number of bars. So for that one there will be one procedure, number of bars, which is denoted with n. So the formula will be capital AST by small AST. So here capital AST means whatever the area of the steel obtained here, that is 275, and what about this area of the steel, that one will be pi dia square by 4. So area of the steel will be pi dia square by 4 and this capital area of the steel will be 275. And here you can assume, so trial number 1, you can assume dia bar. So minimum number of bar used in the beam will be 8 mm. So already I used to told that for hanger bars you can provide 8 mm. It is better to take 10 dia bar, 12 dia bar, 10 bars starting for the tension reinforcement. So check the value for minimum number of bar will be 10 mm dia. So that procedure will be 275 by pi 10 square by 4. So how many number of bars obtained for this one will be, you please simplify, you will get that one. So I will tell you the values. You will get some 3.50, means there is no 3 bars. You can go to the next number, that is 4 bars. So if you are preferring this 10 dia, and again that is better to check another dia bar also, that is 12 mm, and again area of the steel will be equal to 275 and small area will be pi dia square by 4, and again simplify this one, how much you will get, for me it will getting 2.43. So there is no 2.43 like that. Go to the next number, that is 3 bars. Means what is the conclusion here, means if you are using 10 mm dia bar means provide 4 bars, means providing 4 bars of 10 mm diameter. Okay, 10 mm diameter bars. Okay, if you are using 3 bars means provide 3 bars of 12 mm diameter. So this is the way for finding the number of bars required for the sufficient beam. And again after finding this one, you can choose the overall area of whatever the bars you will get. So area of the steel will be equal to 4 into pi d square by 4. So 4 and 4 will be cancelled, pi 10 square, so pi into 100. So that one will be equal to 314 in mm square. And again here area of the steel will be equal to 3 into pi d square by 4. So simplify that one, you will get 3 by 4 into pi 12 square, which is 144. So if you simplify, you will get 339.12 mm square. So here your area of the steel will be 275, and here we are choosing number of bars to provide in a particular beam. So I am taking from 10 mm trials like that. If you want, you go for some 16 dia bar also. So if you go for 16 dia bar means maybe there is a chance of getting 2 bars of 16 mm dia. Then the area of the steel also, if it will be more than this 275 means, more than the 275 means you can prefer here also 2 bars of 16 mm dia also. So based on your availability and requirement, whatever the bar you want, you can choose that one. And again, so what are the spacing in the horizontal and horizontal spacing and parallel reinforcement, I already explained while explaining the concept also. So you can choose the number of bars like this. So here I am choosing 3 bars of 12 dia bars. If you want, you can provide 4 bars of 10 diameter also, no problem. But here I am choosing 3 bars of 12 diameter. So therefore, provide 3 bars of 12 so this is 12 diameter. So therefore, area of the steel required is 275 square, and area of the steel provided is 339.1 square. So already we calculated both of these two. Okay, and almost all we know that we are only calculated up to now here. So if you consider this is a beam, so up to now we are calculated only the beams in the tension reinforcement like this. So here we provided 3 bars like this, but to resist a beam we need hanger bars also, because this is a singly reinforced beam. So therefore minimum we are providing 2 bars. So that is, these two are the hanger bars. So therefore provide 2 hanger bars of 10 diameter, whatever the, so minimum I told you take 8 10 like that. So here I am providing 10 diameter bars in the hanger compression side also. So this is a singly reinforced beam, therefore I am providing 2 hanger bars on compression side. Then after knowing this one, then go for the next step, which is shear reinforcement. Check for the shear reinforcement. Check for shear. Check for shear. So always remember, if you want to calculate shear reinforcement, so see here in the code book, limit state of collapse shear. So that is tau v will be equal to Vu by Bd. Okay, tau v will be equal to Vu by Bd. So here write down the formula as it is. Tau v will be equal to Vu by Bd. So already we people know B and D. And what about this Vu? That Vu will be equal to, so what is the formula? For example, on a simply supported beam, an uniform distributed load is there. So your maximum bending moment will be equal to WL square by 8. And what about the shear force here? That is WL by 2. WL by 2. For example, if a point load means W by 2. For example, if a, so here it will be WL by 2. Here also it will be WL by 2. For example, if a point load is acting means that is W by 2 and W by 2. If an eccentric load is acting means it is at a distance of A means WB by L. If it is at a distance of B means WA by L. So like that, here the formula will be WL by 2. So already we people know what is W into U value. That is 10.5 into, what about the effective span? So the effective span will be 3.16 divided by 2. So if you find out this one, you will get Vu will be equal to 16.59 kilonewtons. Okay. So then find out the nominal shear stress, that is tau v. So what we see in the code book here, that is your tau v will be equal to Vu by B into D, that is B into D, not prefix D. So therefore 16.59 into 10 to the power of 3 in terms of mm divided by B will be 160, sorry, width of the support will be 200 into 160. So that one will be equal to overall 0.51 Newton per mm square. So that is tau v equal to 0.51 Newton per mm square. So then your tau v will be Vu by Bd will be equal to 0.51 Newton per mm square. Then according to the conditions, so read out the conditions. Here, before going to the design, I will show you some important note points for the shear reinforcement consideration. So, design of shear reinforcement. So, first calculate the factored shear force in the beam. So, already we find out here, that is Vu equal to some WL by W into L by 2. Based on that, already we find out that one. And again, tau v will be equal to Vu by Bd. After calculation of tau v, then calculate the percentage of tension reinforcement at the section. Obtained design strength of the concrete will be tau c, which was in table number 19 in IS 456. And again, so go for the condition, that is percentage of steel, which was in IS 456 table number 19. See here, this is the table number 19 in IS 456. If you observe very clearly, if you want percentage of steel, that one will be equal to 100 AST by BD, and we can check the conditions for M20 grade concrete. So you first find out the percentage of steel, that is PT will be equal to 100 area of the steel by B into D. So what about this 100 into AST? So already we people know that we provided area of the steel will be 339.1 mm square divided by B into its D, which is 160. That one will be equal to 1.05. So here your percentage of steel will be equal to 1.05. So based on this, you have to read out that tau c value in the table number 19, which was in IS book, that is page number 73. So that is page number 73 in your IS book. You please read out this tau c value for M20 grade concrete. The percentage will be 1.05. So see here, the value will be for 100 area of the steel, that one will be 1.05. So here it will be in the range of 1 to 1.25, and for M20 it will be in the range of 0.6 to 0.67. You please take down the values as it is. So PT value and for M20 grade concrete, so the value it will lies in 1 point, we want 1.05. So it will be lies between 1.05 to 1.25. So for 1.05 the value will be, so here 1 point m 0.60 to 0.67. So that value will be 0.62 to 0.67. So whatever the value you find by using interpolation or any other scale method, you will get the value which is more than 0.62 and less than 0.63, maybe mid value of these two. But here if you observe very clearly, what happens means, here tau v value will be 0.51, and if you obtain this tau c based on this percentage, so for one only it will be 0.62, means if you calculate for 1.05, also it will be 0. Some 62563, whatever the value. Okay, so more than 0.62 means, if you compare these two, means for one itself it will be lesser than tau c. Okay, for one itself it will be lesser than tau c. Sometimes your tau v value will be some 0.63. At that time we don't know whether it will comes 1.05 comes above below the tau c and above the tau c. At that time you used to calculate. So here I think no need to calculate this tau c. Why? Because for one itself it will be lesser, and if you calculate for 1.05 means almost it will be less. So therefore here the condition will be tau v less than tau c. So that is our condition. So according to this condition, if your tau v will be less than tau c, then you have to provide minimum shear reinforcement. Provide minimum shear reinforcement. Shear reinforcement. And again, I will explain the conditions also here itself. So the first condition is if tau v less than tau c, provide minimum shear reinforcement. So I will explain that topic in our problem. Why? Because our condition is this one only. Sometimes tau v tau v greater than tau c and tau v less than tau c max. So for example, if tau v less than tau c means directly prefer minimum shear reinforcement. What is the minimum shear reinforcement? Already I shown that formula. Area of the steel minimum will be equal to 0.85 Fi by Bd something. So like that you have to go for minimum shear reinforcement as it is. So if you get condition tau v greater than tau c, here your tau c will be some 0.62 to 0.65. So for a value of 0.60, maybe you will get 0.65 like that for 1.05. So your tau v will be maybe some 0.7 like that. So at that time it will be greater than this one. Then you can check the condition whether it will be less than tau c max or not. So how can you will check the tau c max condition, which was in the table 20. So if you see here, this is the table 20. Tau c max for M20 grade will be 2.8. So almost 2.8 will be very huge value comparing to this 0.7 and all the things. So if the condition, so if the value satisfy this condition, if the problem satisfy this condition, then at that time you can design the shear reinforcement. Design the shear reinforcement. So based on the formula, that formula will be somewhat different. That means SV will be equal to some 0.87 Fy area of the steel d by Vus. So maybe in the next example I will show you this type of shear reinforcement design. And for example, if in your case, if tau v greater than tau c maximum, so maximum cases it will be greater than some 3 like that, means at that time if this value satisfies that condition, so at that time you better go for redesign entire problem. If your shear will be like this, means you can go for redesign. So you please remember these 3 conditions before going to the shear reinforcement design. So our condition satisfied the first one, that is tau v less than tau c. So we have to provide the minimum shear reinforcement. So according to our class, so we are providing minimum shear reinforcement. So minimum shear reinforcement, which was in the code book, that is page number 48. So page number 48. See here. So this is the page number 48 in Indian standard. So this is the formula, minimum shear reinforcement formula, ASV by B into SV greater than or equal to 0.4, 0.87 Fy. Means we want ASV is total cross sectional area of stirrups legs. So means we have to take down number of bars like that. SV is stirrup spacing. So here we are providing the stirrup only. So we are unknown is here, our unknown in SV only. B is the breadth of the beam and Fy is the characteristic compressive strength. So take down the formula as it is and then go for the shear reinforcement design. So here ASV by B into SV, that one will be greater than or equal to 0.4, 0.87 Fy. So here our unknown is spacing of the stirrups, that is SV. So if you take down that one, after cross multiplying you will get 0.87 Fy ASV by 0.4 into B into SV. And again Fy will be equal to 415 characteristic compressive strength of the concrete and B is width of the support. Sorry, here 0.45 B only, not this SV. And again, what about this ASV? So this ASV will be equal to, so for stirrups generally we are using 6 mm, which is mild steel. So if you want to use some 8 mm means, that is HYSD again in terms 415 or 500. So here we are using mild steel 6 mm. So that too two-legged. So already we people know what is two-legged. So for example, minimum number of bars required for the beam will be some 4. So two-legged means it will be starting like this, and again it will be round off like this, and again it will close. So here it will not getting accurately. So generally what I am showing means two-legged means it will comes approx exactly like this. It will be surrounded the dia bar. So it will comes and start like this, and again it will close exactly like this. So that is the stirrups. Okay, that is two-legged. So some four-legged means it will be different, which is surrounded by some 6 bars like that. So we are providing two-legged 6 mm stirrups. Mild steel means FE 250. So therefore you can use in place of ASV, sorry, here Fi will be goes to 250. Why? Because we are using 600 mild steel. So mild steel, that is mild steel here, that is 250. And what about this ASV? So this is 6 bars of, sorry, 2 bars of 6 mm dia. Therefore 2 into pi d square by 4. So ASV will be equal to 2 into pi d square by 4. So you please simplify that one. So I am taking all the things here. 0.87. Fi is mild steel, which is 250 into 2 into pi d square by 4, that is 2 into pi d square by 4 divided by that 0.4 into 200. So please simplify this one. So you will get spacing of the stirrups SV will be equal to 152 mm. Maybe some approximate calculation somebody will get 150 or 155 around also, no problem. Whatever the value you will get, you please keep that value only. And then after obtaining this one, there will be two more conditions for this one. So that one will be SV does not greater than 0.75 times of D. Means if you calculate this one, 0.75 D is in terms of effective depth, which is 160. So if you simplify that one, you will get 120 mm. 0.75 times of D, that is 120 mm. And again SV does not greater than 300 mm. So these two things will be mentioned in your code book also. I will tell you that class. So in the code book that will be clearly mentioned. See here in the code book, maximum spacing of shear reinforcement. The maximum spacing of shear reinforcement measures along the axis of the member shall not exceed 0.75 D for vertical stirrups and D for inclined stirrups at 45 degrees, where D is the effective depth of the section. So here we are talking about the vertical members, which is does not greater than 0.75 D, and in no case shall be the spacing exceed 300 mm. In no case shall be the spacing exceeds 300 mm. So that is only the conditions what I am taking here. SV does not greater than 0.75 times of D and SV does not greater than 300 mm. So maximum spacing of the shear reinforcement. So it is better to write down those two things also. Maximum spacing of shear reinforcement. So see here, after simplifying you will get spacing of 152 mm. So that is 152 mm. But according to the IS condition, your spacing does not exceeds these two value. So that is 0.75d and 300. So if you simplify, you will get 120 mm and 300 mm. So out of these three, here they are mentioning clearly your spacing does not exceeds 120 mm. In no case it will be greater than 300 mm. So what is the meaning here means? So here you will get the spacing of SV equal to 152 mm. But SV does not greater than 120 mm in our case, and SV maximum in no case it will be greater than 300 mm. So here after simplifying you will get spacing at 152 mm, but here maximum spacing not allowed more than 120 mm. So out of these two, whichever is lesser condition. So here we are providing the spacing of 120 mm. So using 6 mm dia bars at a spacing of 120 mm. So sometimes you will get here some 110 mm like that. In case of 150 it will get 120 means your maximum spacing does not exceed 120 means at that time you can use 110 only. Why? Because whatever the value lesser, but here maximum spacing not exceeded 120 means 120 will be lesser than this 152. Therefore we are limiting this value to 120 and then we are providing this value, this spacing in our design. So after designing of one more problem you will get this thing very neatly. Okay. Then your last condition, which is deflection, that is very simple and easy point. Deflection. So I will find here last step, that is deflection. So that is very important step. Check for deflection. So it is better to write down this formula for the deflection, that is L by D provided will be so according to the formula L by D provided will be less than L by D maximum. So what is your L by D provided? So here our effective span will be 3.16 and again our effective depth will be 0.16 which is 160. So that is the provided value. If you simplify you will get these two will be 19.75 and check the condition. What is this L by D maximum? L by D maximum will be equal to L by D basic into its modification factor. Okay, L by D basic into its modification factor. Again in the modification factors, what are the things you will get? So that one will be L by D basic into KT, KC, KF. So modification factor for tension reinforcement, compression and flanges. So here we are finding only tension reinforcement because of the singly reinforced beam. For example, if we are designing a doubly reinforcements, it is better, it is to check the modification factor for both the condition from the graph, that is tension reinforcement and compression. For example, we are finding some flange beams like T and L means at that time you can check the modification factor of KF also. So that is the reason here that I am designing only singly reinforced beam. Therefore, I am considering L by D basic into its modification factor. In that modification factor also, we used to check only tension reinforcement. So what is the L by D basic value? So L by D basic value for simply supported beam will be 20, which was given in your code book. See here in the code book, the basic values for given the span ratios up to 10 meters will be cantilever 7, simply supported 20, and continuous beams will be 26. For checking the deflection criteria, control of deflection, the basic values will be L by D will be 20 here. Okay, then again, so based on this graph only, we have to find out the modification factors. So for tension reinforcement, percentage of tension reinforcement, modification factor for tension reinforcement, and this is modification factor for compression reinforcement, and this is modification factor for the flange width. So what I shown here, see here, KT, one graph for tension reinforcement, this KC for compression reinforcement, and KF for compression reinforcement. I shown this L by D basic value for simply supported beam, and here modification factor means I used to take only KT because of the singly reinforced beam. If you are designing doubly reinforced beam means you can check the modification factor for both these two, either for tension reinforcement as well as the compression reinforcement. If you are designing any T beams means at that time you can consider flanges also, no problem. Okay, then we are checking only for this one. So before going to find that one, you can see the modification factor which was in the y axis and this tension reinforcement which was in the x axis. See here, so based on this Fs curve only, we are going to find this modification factor. Fs will be equal to 0.58, Fi area of the cross section of the steel required to that of the provided. Based on that, we have to find out the Fs. So here we are going to find that Fs value. Okay, so I will find Fs value here. So this Fs will be equal to 0.58 into Fy into area of the steel required to that of area of the steel provided. So already we people know that 0.58 and steel will be considered for 415. Area of the steel required will be 270. What is the area of the steel required value? 275 mm square. To that of the provided will be 339. If you simplify, approximately you will get 195. So your Fs curve will be 195 curve. So see here in the range. So there will be 290 curve, 240 curve and 190 curve. There will be no 195 curve, but you can check the value in between these two. Okay, like 190 below exactly some approximate value, and again you can relate that value to the percentage tension reinforcement, then definitely you will get the modification factor. So for finding the percentage tension reinforcement, what we have to do? So already based on the table number 19, we find out that percentage of tension reinforcement, that is PT will be equal to some 100 AST by BD while calculating for the shear design. So here I think already we found that one, that PT value will be equal to this 1.05. So for that value only we are going for the modification factor. So Fs 195 and PT 1.05. See here 1.05 means which is 0, this is 0.8 here, and again this is 1.2, but here I am considering 1, and 1.05 means just some distance away from 1, like this somewhere here, and like this I am moving exactly, sorry, here I am moving exactly, and the Fs curve will be passing below these things. So for example, maybe you can assume here and keep a scale and check directly exactly here. Means you draw a curve, one curve which is 195 curve below to this 190 curve, and you can relate exactly 1.05. You keep one line here exactly 1.05 and one curve, draw one light curve here and check the things which is relevant to the y-axis, that is 1.2 below. So if you calculate like that exactly, maybe there is a chance of getting 1.1. Here it will be 1 and here it will be 1.2. In between you can consider the curve also, you will get exactly 1.1 value. So that is the way for finding modification factor for tension reinforcement. Similarly, I will show you the modification factor for KC also, but no need to provide. So if you see here, so there will be 1.50 for value for us. So it is 1.0 and 1.5, mid will be 1.25. You can consider somewhere here 1.05 between these two, and exactly you can relate here. There will be no fs curve for this one, you can directly obtain the value. If you check like this, means you will get 1.2 to 1.3 in between value, you can consider 1.2 like that. So the value for compression reinforcement will be 1.25. Similarly, here the modification factor for 1 will be 1 only. So here we want 1.05, which is greater value. So you can limit that value to 1 only. The final value is 1. Therefore, take down flange value will be 1. But here no need to check all these things for the singly reinforced beam. Just check these two values and you can simplify. Definitely you will get 22. So therefore, your deflection control is satisfactory, means your L by D provided will be L by D less than L by D maximum, means your deflection is safe. So this is the way for finding the singly reinforced rectangular beam design. And after that, so draw the beam, draw the detailing of the beam. So just I am showing roughly here. So this is the beam. Okay, so these two are the width of the supports. Show here continuous symbols, don't close this one. Okay, so here I am providing the reinforcement bar which was in the tension side. That is 12 mm bar, and here I am providing hanger bar. So that is 10 mm bar. These are the width of the supports. So I am justly mentioning like this. So already we people know. So you please, it is better to mention all the things. The width of the support will be 200 mm. Here also it will be 200 mm. And the clear span will be 3000 in terms of mm, and mentioned very clearly all the things. So here, and again the cross section, and already we find out the spacing of the stirrups. So I'm mentioning stirrups with a blue mark. So the stirrups will be like this. The cross section you will get what are the things. So from this edge to this edge, so like this up to the end. So with same spacing only. So like that you have to provide for entire beam. So with same spacing. So whatever the range between these two, so it will be same between these two, like that only. So write down the spacing value. So that is, so what we find out the spacing, we are finding the stirrups of 6 mm bars. We are using spacing, so using 6 mm diameter bars at spacing of 120 mm. So here two hanger bars of 10 mm dia, and this one will be 3 bars of 12 diameter. Okay, so this is the way to mention each and everything in detail for the beam, and at the same time, so provide the effective span also. So it is better to mention effective depth taken from the center, that is 160 mm, and overall depth will be d equal to some 200 mm. Okay, each and everything. And again, if you cut this section, so if you cut the section anywhere like this, okay, so cross section, so you can draw the cross section as it is, which is very similar to this one. in the same way and in the same length. The same way and in the same length. Okay, so here the dia bars, 3 dia bars exactly in the same length, the same line. And 2 hanger bars exactly in the same line. So and provide the stirrups. So this blue color stirrups. So first I am providing the stirrup and then bars, then only it will be convenient to draw here. So you can draw first bars and then stirrups. For me it is inconvenient to draw here. Each and everything will be in the same range and same length only, but it is not convenient to draw here for me. So and the two-legged will be means like that you will get means, so there will be 4 bars means already I showed you, it will taken like this and again comes and closes here like this. So that is the reason I am mentioning like this. Okay, so again this is the cross sectional view of the beam after cutting whatever the section. If you want to please mention all the things in details, B value and capital D value, and here also same bars, 2 bars of 10 mm dia, and this is the stirrup of 6 mm stirrups, 2 legged 6 mm stirrups, and here we are providing the spacing of 120 mm, and here there will be 3 bars of 12 mm dia. So these are the detailing of the singly reinforced beam. I hope you understand this lecture. Thank you so much for watching this video. If you really like this video, please like this video, share it to your friends and subscribe our channel. Thank you so much.